Now we are going to study the drawbacks in intrinsic semiconductors. Okay, so last class we have seen the two types of semiconductors. One is intrinsic, another one is extrinsic. So in intrinsic semiconductors, mostly the classification also we have seen. Okay, that is elemental and compound and many things we have seen. After the intrinsic semiconductors, it is nothing but a pure form of semiconductor. Okay, so the intrinsic is nothing but the pure semiconductor. So what are the drawbacks in this intrinsic semiconductor? Before knowing the drawbacks, we have seen that the intrinsic semiconductors at very low temperature, particularly at 0 Kelvin, it acts like a insulator. So we need to raise the temperature of the semiconductor. So while we are raising the temperature of the semiconductors, there is a possibility of the electrons or the holes to move. Okay, so the electrons or the holes are the charge carriers in the intrinsic semiconductors. So normally it is not, there is no use of fabricating such a semiconductors. So we need to do something. We need to modify something in the intrinsic semiconductors for the good conductivity. Okay, so that is the second type that we'll see in the next topic, that is extrinsic semiconductor. Before going to the extrinsic semiconductor, what are the drawbacks in the intrinsic semiconductor? First one, current is controlled by the temperature. Already we know. At 0 Kelvin, it acts like a insulator. At 0 Kelvin, it acts like a insulator. So we need to raise the temperature of the semiconductor, then only the conductivity will be increased. So by increasing the temperature, the current also increasing. That is, by increasing temperature, current also increase. So the current is controlled by temperature. This is one drawback. Second one, the current is very small. We use the word current now because the electron current and the hole current. So the total current is the sum of electron and hole current we have studied. So the amount of current produced in the semiconductor due to the external factor, which is very, very small, that is limited. Then third one, in an intrinsic semiconductor, the number of holes is always equal to number of electrons, or the number of electrons is always equal to number of holes. But for a best conductivity in a semiconductor, either the electron number should be more or the hole number should be more. So for a best result, we must need the number of electrons should not equal to number of holes. Either the electron must be more or the hole may be more. But in intrinsic semiconductor, then how many holes are produced, that much electrons also there. So the number of holes and number of electrons will be equal in intrinsic semiconductor. This is another one drawback. Okay, so these are the three important drawbacks in a pure semiconductor, that is intrinsic semiconductor. First one, the current is controlled by temperature. At 0 Kelvin, the intrinsic semiconductor acts as an insulator. But at room temperature, there is a conductivity, but it is very, very less. That is limited. Moreover, in intrinsic semiconductor, the number of holes or the electron that is equal to number of holes or an electron. Okay, so the number of electron pair that is equal to number of electron hole pairs is equal in intrinsic. But for a best conductivity in the semiconductor, the electron hole pair should not be equal. So these are the three drawbacks. Next, we are going to see the second important types of semiconductors, extrinsic semiconductor. Listen. So extrinsic semiconductor. Why it is extrinsic semiconductor? Till now we have studied about only the intrinsic semiconductor. So in intrinsic semiconductor at 0 Kelvin, there is no possibility of electrons from the valence band to conduction bands. So it acts as an insulator. So we need to raise the temperature. So by raising the temperature, only the small quantity of electrons moves from one band to another band through the energy gap. So for a best conductivity, there must be do some alter in the intrinsic semiconductor, which means we need to add some impurity. Okay, so by adding impurities, by adding impurities, we can get the extrinsic semiconductor from intrinsic semiconductor. That is, by adding impurities with the germanium or silicon, we'll get extrinsic semiconductor. So we added the impurities, no? So that is in a limited amount. That is called as dopant. Mostly that value should be ppm, which means parts per million. What is a ppm? That is parts per million, which means for every 1 million of silicon atoms, we have to put 3 atoms or 5 atoms. For every millions of silicon atoms, that is, for every millions of silicon or germanium, have to add it's 3 or 5 impurity atoms. So by adding the 3 or 5 impurity atoms, we will get the extrinsic. So we are adding that impurity atom, so that is called dopant. So dopant, what is called dopant? The amount of impurity added in intrinsic semiconductor is known as dopant. So the process is called doping. So what is a doping? It is a process of adding impurities. So the extrinsic semiconductor is also known as doped semiconductors or impurity semiconductor. So there are 3 names. There are another 2 names for the extrinsic. One is doped semiconductor or impurity semiconductor. So mainly we must use the word parts per million, which means for every millions of silicon or germanium atom, we must add the impurities. How much? Whether it's a 3 or 5. If we add a 3, what is the name of the type of semiconductor? If we add a 5 impurities, then what is the name of the particular type of semiconductor? Next we are going to see the other 2 types of semiconductors, that is extrinsic semiconductors. Are you clear? So dopant and doping, almost similar. Dopant is what quantity of the impurity is added is called dopant. So hence the process is called doping. So imagine this is an intrinsic semiconductor. Basically in the intrinsic semiconductors, the current is limited because the current is determined by the temperature. Okay. Moreover, the number of electrons and the number of holes are equal. So we cannot design by using such a intrinsic semiconductor. So we need to do some modification in the intrinsic semiconductor to make them good conductivity. For this, we are adding something. So the addition of something, that is addition of impurities in the particular semiconductor is called extrinsic semiconductor or doped semiconductor, or another one is impurity semiconductor. So in an impurity semiconductor, mainly we should notice that ppm, which means for every millions of silicon or germanium, we have to add 3 impurities or 5 impurities. So depending upon the 3 impurities or 5 impurities, the extrinsic semiconductor is classified into 2 types. What are the 2 types? See that. So one is pentavalent, another one is trivalent. Second one is trivalent impurity. So in a pentavalent impurity, the valency is 5, whereas in a trivalent impurities that has a valency is 3. Okay. So in a pure intrinsic semiconductor, if you add a pentavalent, that is called N type. In a trivalent impurities, actually the trivalent impurities are added to the intrinsic, that is called P type. Okay. So the example for the pentavalent is arsenic, antimony and phosphorus. Arsenic, antimony and phosphorus. Okay. So arsenic, antimony and phosphorus. Yes. Arsenic, antimony and phosphorus. So these are the examples for the pentavalent impurities, and for a trivalent impurities, the example for indium, boron and aluminium. Indium, boron and aluminium. Indium, boron and aluminium. So these have a 5 valency and these have trivalency. Okay, it's a very simple concept. Already we know the germanium or the silicon, which belongs to group 14, or depending upon the valence we can say it is group 4. So in the group 4 element, we are going to dope these impurities, any one of this. Okay, imagine this is covalent bond. This is original atom. So all these are covalent bond. So plus 4, which means it's a silicon or germanium. It is silicon or germanium. So in every cell, it is completely filled. So here you can see that. So in the covalent bonds, the electrons are normally occupied. Okay, listen, plus 4. So already we have seen that this is nothing but silicon or germanium atom, and the dotted lines are indicates the covalent bond, and the electrons are there, the valence electrons are there. Okay, so it is a strong bond. Okay, now we are adding the impurities, that is pentavalent. Pentavalent is nothing but arsenic, antimony and phosphorus. So by adding the pentavalent impurities, penta means 5. So in the 4 electron are uniformly bonded with this, then another 1 electrons are left extra. So it have 1 extra electrons, right? So this is called donor atoms. So the structure looks like this. Imagine. So in this structure, it has 1 extra electrons, and this is donor atom. So it have one extra electron. So these extra electrons are electrons are the majority charge carriers. Okay. So while we are doping the pentavalent impurities with the pure silicon or germanium, we will get N-type semiconductors, which means the electrons are excess. So these electrons are the majority charge carriers in the N-type semiconductors. Okay. So even it does not depend on the heat. Even the small quantity of heat also there, but we cannot alter the number of electrons. So the number of electron is more in the semiconductor comparing to number of holes. Okay. So this type of semiconductor is called N-type semiconductor. So N-type semiconductor. So in N-type semiconductor, the electrons are majority charge carriers. So here you can see that normally in a silicon or germanium atom, we are doping the pentavalent impurities. By doping the pentavalent impurities, the 4 electrons in this pentavalent completely bonded with the other 4 covalent bonds, and it has extra 1 electrons. Okay. So these electrons are mainly responsible for the conductivity. Okay. So the electrons are the majority charge carriers. Suppose instead of adding the pentavalent impurities, if you add a trivalent impurities, what will happen? See. So in an N-type semiconductor over, next one is P-type semiconductor. So in a P-type semiconductor, we must add the same structure. You see that. So this is atom, silicon or germanium atom. It has all the silicon or germanium atom. Now we are adding the impurities, but that is trivalent. But already +4 is there. Okay, this is our +4. All this +4, and here also +4. But while adding the trivalent, 3 electrons are bonded with this, and for another 1 electron there is no place. So here the vacancies are created. Here the vacancies are created. So here vacancies are created. So it must require 1 more electron to complete. So it wants to receive electrons from the neighborhood atoms. So here in the P-type, in the N-type, that is a donor atom because it has 1 extra electrons. But in a P-type, this is acceptor atom, and it has holes. So in N-type semiconductors, electrons are majority charge carriers. But in a P-type semiconductors, holes, because it must require 1 more electron to occupy. So it have vacancies. Holes are also called vacancies. So holes are majority charge carriers. So in a N-type semiconductor, the number of electron is more than the holes, but in a P-type semiconductor, the number of holes are more in number comparing the number of electrons. Okay. So how this diagram modify? Listen, we can modify the diagrams for P-type semiconductors. We are adding the trivalent impurities. So it need 1 extra electron, so that place is empty. So we have only holes. Okay. So this is energy band diagrams. So depending on that, next we are going to see about the how to form a PN junctions. Okay, so we know the N-type semiconductors and this one is P-type semiconductors. Next we are going to form PN junctions. So how to form a PN junction? Okay. Now we are going to see the energy bands in the N-type semiconductor and the P-type semiconductor. Actually, we'll have to see PN junction formation, but before seeing the PN junction formation, we'll see the energy bands, how it looks in N-type semiconductor and the P-type semiconductor. Already we know from N-type semiconductors, electrons are majority. Electrons are majority. Similarly, in the P-type semiconductor, holes are majority. So we know in a semiconductor there are two bands. One is valence band, another one is conduction band. Here they represented the valence band energy level and the conduction band energy level. Okay. Here additionally they mention donor energy level, because the donor energy level because it's always have one extra electron, so it's being positive. Already we know the structures. So in this case, it is a +5 we added. So remaining are +4, so silicon and germanium. So it have one extra electron, so we can say it is the donor atoms. So the donor energy level is totally different from the PN junction. In PN junction, it is acceptor energy level because it needs one more electron to receive. So it have the holes. Holes are the majority charge carriers. But the energy in the energy bands in P-type, the acceptor energy level is different position comparing the donor energy levels in the N-type semiconductors. In N-type semiconductors, the donor energy level is always lies very close to the bottom of the conduction band. This is conduction band. So it's all conduction bands. These are all valence bands. So the donor energy level that is being positive, the donor energy level is lies at the very close to the bottom of conduction band. And from this donor energy level to the original conduction of the energy band, it is approximately equal to 0.01 electron volt. Okay, so it has the excess electrons. So the electrons are the majority charge carriers. Since the most initially it has no electrons, but when the temperature is raised, that is T is greater than 0 Kelvin, when a temperature is raised, what happens? Most of the electrons are coming from the donor atom that will occupy the conduction bands in the energy levels. Okay, so there only in a conduction band energy levels, the most initially it is empty, but how this much electrons are coming now? The most of the electrons are coming from the donor impurities. That is, what is the donor impurity? Trivalent or pentavalent? Pentavalent. So when a pentavalent substance are added to the pure form of intrinsic semiconductor, we'll get N type of semiconductors. So this is how the energy bands look in N type, and this is the original. This is the original conduction band and the valence band. So the valence bands are separated from the conduction band by the energy gap. This is the energy gap between the valence band and the conduction band. So the valence band and conduction bands are separated by the energy gap or forbidden energy level. This is also called energy gap. Okay. Or forbidden energy levels. So what is the forbidden energy level? How it looks, we'll see in the upcoming topic. Okay. So I repeat once again. Mainly we should notice the donor energy level, because in N-type semiconductors, the donor is always being positive because it have one extra electron, and the most of the electron occupies the conduction band. All these electrons are coming from the donor impurities. Okay, so here the holes are less, electrons are more. This is the only one holes we have. Okay, that is somewhere else, but most of the things are electrons. So all these are electrons, and in the conduction bands mostly occupied, it is due to the impurities donor atoms. Okay, but it is totally opposite to the p-type semiconductors. P-type semiconductor can be formed by trivalent impurities. Yes. So here it is plus. So the holes, most of the holes resides in the valence band. Because it have vacancies, it needs electron to receive. So the holes remains in the valence band. Only very few energetic electrons alone able to rise up. So the acceptor energy level just opposite to the previous case. In the N-type semiconductor, donor energy level lies at the bottom of the conduction band, but in the P-type semiconductor, the acceptor, it is always negative because it have vacancies. So the acceptor is negatively charged. So the acceptor energy level lies at the top of the valence band, which is very close to the valence band. Moreover, it is located at the top of the valence band, and this is for energy gap, forbidden energy gap. Okay, so why like this formation means it is due to trivalent impurities. Trivalent impurities. So because of the trivalent impurities, it looks like this. And at equilibrium, what will happen? At equilibrium, listen, and this is also by raising the temperature, T is greater than 0 Kelvin. Mostly at room temperature or more than room temperature. At equilibrium, the product of the number of holes and the number of electrons is equal to at equilibrium, the number of electrons and number of holes, which is always equal to number of, that is a square of the number of carrier intrinsic concentrations. Okay, number of carrier intrinsic concentrations. We know the group 4 elements. Okay, what are the 3 elements? It is a carbon, silicon, and is germanium. So these are all belongs to group 4 elements depending upon their vacancies. Okay, so for carbon, the energy required is 5.4 electron volt, and for silicon it is 1.1 electron volt, and for germanium it is 0.7 electron volt. So that only the carbon has more amount of energy, so it requires more ionization energy. So mostly we cannot use carbon to fabricate the semiconductors. So we may use silicon or germanium to fabricate semiconductors. The next topic is formation of Pn junction. Okay, now we are going to see the Pn junction because most of the semiconductor have uses the Pn junction. So how to fabricate the Pn junction formations? It's a very simple thing. So to form the Pn junctions, we must require a thin p-type silicon wafer. Okay, this is p-type silicon wafer. It's a very thin slice of the p-type silicon wafer in which we are going to inject a pentavalent impurity. Actually, there are many processes, but simple process is given here. That is the formation of Pn junction. To form the Pn junction, we have many processes, but the simple process is by taking a p-type silicon vapor, in which we are injecting the pentavalent impurities. By injecting the pentavalent impurities, because pentavalence means that it have extra electrons. So one side it forms full of N because there it has the partially charged things. Okay, which means the electrons are more, and another one side the holes. So which means it is a donor atom. This is acceptor atom. It's a very simple thing. So once again I repeat, by taking the p-type silicon vapor, we are adding the pentavalent impurities, in which one side it forms a p regions, another one side it forms a n regions. There is a metallurgical junctions between them. So it forms a metallurgical junctions between them. Between the p-type and the n regions. So to form the Pn junctions, the two important processes are diffusion and the drift. Diffusions and the drift. Actually, once we have formed the junction, at the time to form the junction, what will happen? From n side, okay, look at from this pictures, from n side, the electrons are the majority charge carriers, no? So the electrons started moving towards the p side. Okay, it has extra electrons, so the electron diffusion takes place first. At the same time, the hole also started to diffuse, just to balance the places. So the holes are moving towards n side. Okay, so electron diffusion towards p region, and the whole diffusion takes place towards n region. So this is diffusion. So diffusion means the diffusion of electron from n to p, and the diffusion of holes from p to n takes place. So because of that, there is the depletion layer, the layer which maybe reduces. Okay, but it will be balancing. But before reducing, the next one is drift. What is called drift? So the electron reached there, no? So the electrons started to move again to which side? N side. So electron drift towards n. At the same time, the holes drift towards p side. Okay. So under equilibrium, the number of electrons and the number of holes will be equal. So that only we need to supply the external potential. If you supply the external potential, that will maintain to move the electron further from n region to p region, and the holes from the p region to n regions. So there is external voltage is required to maintain the electron movement or the hole movement. So the particular potential is called barrier potential. Next one is barrier potential. So what is the barrier potential? The barrier potential only prevents the electron further moving from n region to p region, and the holes moving from the p region to n region. So it looks like this. This is a barrier potential. So from the barrier potential, that is V0, barrier potential. So the barrier potential used to prevent the electron movement from n to p side and the hole movements from p to n side. But under equilibrium, both also equal, and there are two important processes. One is the diffusion, another one is drift. Diffusion, already you know that potato osmosis you have studied, no? Yes, the sugar solutions that diffuses through the layer and reaches the water. After some time, the water also becomes sweeter. So similarly, this region, like it acts like a semi-permeable membrane. Actually, we used to say as depletion layer, deplete, reducing. Okay, during the supply of the external voltage, the layer width is reduced. W means the width of the depletion layer. Basically, the width of the depletion layer reduces by the external potential. Okay, so at the time it reduces. So by supplying the external potential, we are injecting two different things from the either side. One side we are injecting the electrons, another one side we are injecting the holes. So electrons are injecting one side and holes are injecting another one side due to the external potential. Okay, So due to the external potential, the electrons from the p side and the holes to the n sides are ejected to reduce the width of the depletion layer for making the semiconductor more conductive in nature. Okay. So I'll repeat once again how to form or how to fabricate the PN junction. It's very simple things. We should take only the P-type silicon vapor completely. Imagine this is a P-type silicon vapor. In this, we are going to inject the pentavalent impurities. By injecting the pentavalent impurities, it have extra electrons. Okay. So these extra electrons, this side become donor level and this side become acceptor level. So the extra electrons from the n side started diffuse to p region. At the same time, the holes started diffusing towards n side. So if diffusion happens, drift also occurs. So drift from the electron drift from the p to n side, because n side become completely it's a negative, so electrons are needed more, and p side needs a more hole, so the hole drift towards the p. Okay, so the width of the depletion layer can be maintained by the barrier potential, because under equilibrium the number of holes and the number of electrons both will be equal. So we need to maintain the further movement of electron from n side to p side and the holes movement from the p side to n side. So that can be done by the barrier potential. Okay. Next, about the PN junction, forward bias and reverse bias. Before seeing the forward bias and reverse bias, first how to form the PN junction we have seen. Okay, with a pure form of P-type silicon wafer, we are added the pentavalent impurities. So one side become N region, another one side become P region. So the PN, this is P, this is N, and this is depletion layer. So the width of the depletion layer and this full of P, this full of N, this with connected with the metal ends to an external applied voltage is said to be PN junction. So the symbol of PN junction is very simple. Actually, the symbol looks like this. So the arrowhead, which means a P, and with the vertical lines, this means IN, connected to the external voltage. Okay. So the PN junction formation is very simple. The P region and N regions at the ends are connected with the thin metal plates and connected to the external battery or external potential. And this is a symbol of PN junction. So here the arrowhead, that means a conventional direction of current. The arrowhead means a conventional direction of current. So opposite will be the N junctions. Now PN junction under forward bias, under reverse bias we are going to see. Listen. So first we will see the forward bias. So usually we should connect a battery. So P side is positive, N side will be the negative. No. So the positive terminal of the battery is connected to P side and the negative terminal connected to N side. So this is a external battery. Okay. So to measure the potential difference across the PN junction, the voltmeter need to connect parallel to the junction. Okay, this is voltmeter, but ammeter should connect in series. So we need to connect the ammeter. So to connect the ammeter to measure the current. So this is ammeter. So this is ammeter, and a key is also used here. This is the key. Okay, so ammeter and battery and diode is in series. voltmeter alone connected across the circuit. Okay. So this is likewise only we should do the forward bias. So in a forward bias, initially already we have seen that in a Pn Junction formations, the amount of holes and the amount of electrons will be the equilibrium. So the external potential is needed to maintain the number of holes further moving from P to N side and the number of electrons further moving from N to P side. Okay. So important thing we should notice here, that is the direction of the applied voltage is opposite to the built-in potential. So the direction of applied voltage is opposite to built-in potential, that is V naught. Initially we are considered only the battery terminals are connected, only one cell we are used. Okay. So at the time the voltage across the junction is maintained by the voltmeter and the current through this junction maintained by measured by the ammeter, but the amount produced is very less, only the milliammeter, that we can say MA, milliammeter. This is a key. Okay. So the barrier potential diagram, you see that, look at the diagram. So initially the battery terminal is 0, so no current flows. Gradually the applied voltage is increased. The applied voltage is increased, 0.2 voltage to 0.4, 0.4 to 0.6. So further the 0.6, suddenly from a point, the current value gradually increases. It comes like this. The graph comes like this. In a forward bias, when a voltage is increased at a particular certain applied voltage, the current also suddenly increases. This is said to be forward bias. Okay. So in a forward bias case, mostly the direction of the applied voltage should be opposite to the built-in potential. How? Listen. So just battery is connected. So just battery is connected. If you increase the applied voltage, the width is reduced. That is the meaning of it. The inbuilt potential is opposite to the applied voltage. If the applied voltage is increased, the inbuilt potential is reduced, which means the width of the depletion layer. The Pn junction, no, in a Pn junction diode, this is initial width when the battery is connected. If the applied voltage is increased, then the width also reduces. Then the further and still reduces. Okay. So likewise, this is for 4 and this is for 6 and this is for 7. Okay. So no applied potential and 0.2 voltage, 0.4 voltage, 0.6 voltage. So you can notice that the width is gradually reduced. So if you apply the more voltage, then the electrons gradient, okay, electron gradient takes place. The electron gradient is nothing but injection of the electrons to P side and the injection of holes to N side. Okay. So by injecting the holes and the electrons to the corresponding regions, the width of the depletion layer is reduced, comparing the initial. This is initial case, now it is final case. So there is more possibility of the current in the circuits. So the current produced is only in milliampere. So only in milliampere. Okay, this is ammeter, it is in milliampere. So suddenly after the 6, you can see that it gets break down and it raised further. Okay, so this is the forward bias. But in a reverse bias, just opposite. Okay, we should do only one small changes. We need not to alter anything. Only the two things we alter in the reverse bias. In a reverse bias, and one more thing I forgot to say, in a forward bias, the minority carrier injection could be done. So the PN junction forward bias is also called minority carrier injection, and the reverse bias is majority carrier injection. Majority carrier injection. Listen. In the forward bias over. So the reverse bias, just we need to change the battery terminal. Instead of positive, we have to connect the negative terminal to the P side, and the positive terminal have to connect it to N side. Okay. And another one changes, the ammeter not be taken in milliampere range, it's microampere range we should take. Okay. And repeat the experiment, reset everything. Once again we need to start. So now using the rheostat, gradually increase the battery voltage. But you notice this is the initial case. This is the initial case. But now what will happen? This is initial case of the barrier potential. The width is increased. So this is the initial width. By applying the external voltage, the width is increased. In the first case, width is reduced. Now width is increased. The width of the depletion layer is increased by giving the external potential. This is for a second case. So here first means only with the battery, but no voltage is applied. But here voltage is applied to this PN junction under reverse bias. Okay. So the current value is almost close to the same axis, but further one point it suddenly breaks down and it increases. But the current measured here is in microampere. Current measure is microampere, and the particular point from which, for the particular point of the applied voltage, the current is suddenly increases. This is called as breakdown voltage. Which means for a particular applied potential, suddenly the current in the PN junction increases in negative region in microampere scale. That is called as breakdown voltage. So the forward bias, and this is for a reverse bias curve. This is for a reverse bias curve. So the combination of the both is called IV characteristics. So this graph is called IV characteristics curve of for PN junction. Okay, so this curve is very, very important, and you are going to perform the experiments in your laboratory using the PN junction. But only one topic is deleted from this lesson, that is Zener Diode. So Zener Diode, that is application is totally deleted. So the Zener Diode we are not going to learn. Only the PN junction diodes and its characteristics curve. This is the characteristics curve. You should notice the characteristics curves. Two things we should notice. One is in forward bias, the current value is in milliampere, whereas in the reverse bias, the current value is microampere. Okay. And one more thing is breakdown voltage. What is the breakdown voltage? Under the reverse bias of the PN junction, for a particular applied voltage, suddenly the current value increases. So a point from which the current value increases to the applied voltage is called as breakdown voltage. Thank you.